All right, today in Unit 15, Unit 6, Chapter 15, we're talking about the reaction quotient, which is symbolized by the letter Q. And Q is basically found the same way you would find an equilibrium constant. So you have the setup of, the concentration of products raised to their coefficients divided by the concentration of reactants raised to their coefficients. But if we have non-equilibrium conditions, instead of referring to it as the constant, because it's not a constant value, we call it Q, the reaction quotient. So when we would want to assess Q is if we're looking at trying to figure out, are we at equilibrium, if we're not told that specifically. Also, when we're working some of our other equilibrium problems that we've looked at, we've seen the scenario where we start with only reactant amounts. That makes sense. You have a reaction, start with reactant amounts. We know the system's reversible, or the reaction's reversible. We do reproduce some of the reactants as we go. But, normally you just start with reactants. Well, there are some scenarios where we've got a reversible process where we end up starting with both the reactant species and product species for whatever reason. And we need to assess, well, where is the system going to go in order to get equilibrium? And I'm going to say, where's the system going to go? What I really mean by that is, do I need to make more products to get to equilibrium? Do I need to make more reactants to get to equilibrium? And, especially if we're trying to look at that change row in our ICE table, it's pretty important to make sure that we recognize, am I going to be reducing the amount of products and making more reactants to get to equilibrium? Am I going to be reducing the amount of reactants and making products to get to equilibrium? And so that's what the Q value can help us to assess. Are we at equilibrium? And if we're not, what's the system need to do to get there? All right, so if we take a look down here, this kind of summarizes what Q can tell us. So again, we're writing our equilibrium constant expression exactly the way that we've done before. We're plugging in the current values that we have, and we're looking at how does that value of the reaction quotient compare to the constant. If the reaction quotient is less than the constant, then basically, again, if we're looking at this products over reactants ratio, that's what these values are both equivalent to. Well, if this is smaller than it would be at equilibrium, that means that I need to make more products to get to equilibrium, right? So that would mean that the numerator needs to increase, the denominator would need to decrease in order for us to get a ratio that is equivalent to the constant, which happens to be a larger value than where we've currently assessed things. If we have the reaction quotient equal to the constant, well, that means that you're at equilibrium. It's nothing that's going to change. Again, we have the forward and reverse reactions continuing, but our concentrations are not going to be any different over any period of time. Opposite of what we previously described is true if the Q is greater than the constant. So again, looking at this ratio of products over reactants, that would tell me that currently the product concentration is higher than it would be at equilibrium. The reactant concentration is lower than it would be at equilibrium. And so that means that we're going to be increasing the amount of reactants. So that reverse reaction is going to be driving forward, and the amount of products will be decreasing overall. And again, this process will happen until my ratio of products over reactants ends up equaling the constant, and then we'll be at equilibrium. So let's take a look at when we would need to worry about this, when we want to assess this. And so take a look at one of the problems that we have on one of our worksheets. Okay, so here we've got a reaction described between carbon monoxide reacting with steam, producing carbon dioxide and hydrogen. And so I've got the balanced equation written out here. So I've got carbon monoxide as a gas, H2O as a gas, and that's reversibly producing carbon dioxide and H2 as a gas. And so we're told the equilibrium constant is 5.10, and we're told that we have 1 mole of each component in a 1 liter flask. So again, we want to work in terms of the concentration version of the equilibrium constant. So in terms of molarity, since we're dealing with a 1 liter flask, I'm going to be referring to the mole amounts as molarity since it's all per 1 liter. So the idea here is that if I look at my initial amounts, we've got 1.00 molar for each of these species. So we're not just starting with reactants, we're starting with some reactants and some products. So what we're going to need to do before we can look at this change column, or change row, is assess, well, are my reactant amounts going to decrease? Are my product amounts going to decrease? Because if we're talking about the X change that we've used in previous problems, what we need to talk about, is it going to be a positive X or a negative X for the reactants or for the products? So let's take a look at what I mean by that. So we're just going to pretend we don't see this other problem right here, right now. Let me write out my expression down here. So I've got concentration of CO2 times concentration of H2 divided by concentration of CO times concentration of H2O. And currently, if I plug in everything as 1.00, well, without doing any complicated math, 1 times 1 divided by 1 times 1 equals 1. So right now, Q is equal to 1. Okay, so this value is less than the constant. They told me the constant is 5.10. So what that means is that my system is not at equilibrium, and in order to get to equilibrium, what that means is that my numerator amounts are going to have to increase, these denominator amounts will have to decrease, and in making those changes as such, the Q value will approach the constant, okay, as it gets to equilibrium. So that means then that just like we've seen in our other problems, when we are looking at the change, the reactant amounts are going to decrease. So let's say there's some change by some X amount, and these are all coefficients of 1, so these would all have, so these are going to go down by some number of X, and the product concentrations are going to increase by that same value of X, and then we can do our equilibrium amounts. Okay, and so if I scroll down to some blank page here, okay, so what that means is that we've got 5.10 is the equilibrium constant, and we've got for our product concentrations, we've got 1.000 plus X, and that was the same for both of them, so I'm just going to write squared on there. And then for the reactant concentrations, those are going to be decreasing by that same amount of X. And again, there's 2 of them, so that's why I'm squaring them, just to save myself some space. So conveniently enough, since we've got the top and the bottom that are squared, we can take the square root of both sides to get those squared terms out of here. And then we just algebra it up, so we end up with 1.00 plus X divided by 1.00 minus X, and that equals 2.258. And if we rearrange and solve everything, and you can pause this and do that for yourself if you want to check to make sure you can do the math, you end up with X equals 0.386, and again that's going to be molar. So if we plug that back in up here and solve for our equilibrium amounts, then again, if we subtract that off from the reactant amounts, that gives us 0.614 molar for those. And we've got 1.386 molar for these then. Oops. And of course, if we double check, just plugging these values back into the expression, we do then with these amounts get the constant when we plug them into the expression. And so again, how this problem would vary if the initial conditions were different, well, let's just pretend that we were given an initial concentration for carbon dioxide, or sorry, carbon monoxide. Let's say for the reactants we were given 0.500 moles per liter, and for the products, let's say we were given 1.500, just to change things up. So let's say the problem was different and these were the starting amounts that we were given. Well, the plugging these values into the expression, we would end up with, let's get rid of this problem, sorry, this is going to be Q. We would get 1.500 squared divided by 0.500 squared, and that would come out to, geez, I should have done my work and written this down ahead of time, but that comes out to 9. Okay, so that's obviously greater than the constant. So if these were our starting concentrations, what that would mean is that my product amounts are too high and my reactant amounts are too low for the system to be at equilibrium, and so the reaction is going to proceed to the left, meaning we're going to make more reactants and use up some of the products in order to get ourselves to equilibrium. So if this were the case, if these were the concentrations we were given to start with, when we filled in this ICE chart, what would have happened is we would have had to have put, this would have to be negative X for the reactant amounts, because we would be using up, sorry, for the product amounts, we'd be using up the products and we would be forming more of the reactants. And so again, this is why you would need to figure out Q and figure out the current position in relation to equilibrium. And this is also going to be something that's very, very important when we are looking at Le Chatelier's principle.